Hi everyone, and welcome to BioVCN's Python channel lesson 8. This is a continuation of our tutorials on the Python Pandas data frame library. So this will be part 2. I'm going to pull up the README on my screen quickly. Now at this point, you should see the BioVCN website with the README for Pandas part 2. So what I want to do this lesson, now that we've established some of the basic syntax and usage of Python Pandas, is to show how in a practical workflow these functions are actually used, as well as to teach some of the more advanced functions and advantages of the Pandas library, like multi-indexing and functions such as group by. So first, I want to give you a little bit of context for the data we're going to examine and manipulate. So this is an OTU table and a metadata table from my own fieldwork at Fayetteville Green Lake in New York, which is a stratified lake. And this is in particular the OTU table for my particle-associated DNA. So I think that a good task for us to utilize some of these functions is to clean up our OTU and metadata tables, isolate a particular group of OTUs we're interested in. In this case, it'll be photoautotrophs, and to examine those abundances in relationship to the relevant metadata. So I'm going to click on the launch pad and our binder should load. Okay, so now in our directory, we can see this Python notebook, Pandas part 2, which we're going to open. And now we see our notebook. So the first thing I'm going to do is import the Pandas library as PD. And next, let's import our OTU table and the metadata table associated with it. Now let's take a look at their structure. So for the OTU table, you'll notice the way I've imported it with the CSV function, I've designated the index column as OTU ID. So if we take a look at it, we see here all the indices or the OTU IDs in bold on the left-hand side. And then we see the actual sample IDs as the column headers, and then the count information as the data. So now I'm going to clear that. And let's take a look at the metadata structure. This is going to be something new. So if you noticed when I imported it, rather than designating an index column, I've designated header equals 0, 1, which refers to the first 2 rows of that CSV file. And that will create multi-indexing. So let's see how that looks. So I haven't actually set a row indexing system yet. So Pandas by default will go with iloc or numerical. But here we have our column headers, but then above that, notice that there's 3 other headers: index, continuous, and categorical. And that is going to designate each of the columns below it as a different type of column header. So I'm designating sample ID as index, the depth column as continuous data, meaning that I haven't binned it into some categorical scheme. And the remainder of these, sulfide, particulate, sulfur, and so on, are all categorical. Now, ideally, what you want when you have multi-indexing is to have this sort of setup, but with some sort of row indexing. In this case, I like to use sample ID or OTU ID usually. And I found that it's kind of a quirk of Pandas that it's not particularly easy to set when you have a multi-indexed setup. So here I've illustrated how to do that. So I do metadata equals metadata set index index, which is saying in this column that I've designated with the higher indexing as the index column, set that as index. But I actually found that when you do it that way, when you have multi-indexing, it returns a weird format of a tuple, which remember it's two values enclosed in parentheses. So this loop is supposed to fix that. So I'm actually declaring an empty list here, and I'm saying for each of those indices, take the first item in that tuple and then reset the index column. So let's run that. And now if we look here, we see exactly what we want. So the sample ID has been set as the row index column. And that's going to become important when we actually want to match the metadata information to OTU information by using the sample IDs. And here I'm just describing that. So now what I want to introduce is how to actually use multi-indexing. You can actually slice along your indices at varying levels using the function metadata.xs. So xs, the syntax is in the parentheses, you have your index category followed by your index level and your axis. So here I've given an example to say, okay, take my metadata column and find at the higher index level, or that first row of column headers, along axis 1, meaning columns, give me everything that's classified as categorical. And you see how useful that is. So if we compare our output here, you see that it excludes the depth column, which is not categorical data. This can be really useful if you're doing a metadata analysis where you're doing some sort of statistics and you need to reduce all your continuous data to categorical data first. Now, if you want to access a particular data column at that level, you simply use the standard Pandas structure where you then follow that with your column name. So in this case, I'm putting sulfide. And you'll see here, this is all the sulfide data. The indices are on the left. And you see here that the name is shown as sulfide. Now, if I actually, the weird thing about slicing with multi-indices is that if you were to try to access sulfide by the column header directly, you would not be able to just put sulfide in the square brackets. You have to actually specify that you're at that lower level, which is what I've shown here. So you see if I do that, I have all my data here, and then it shows the other multi-indexing header on the top. Okay, so now that I've gone over that a bit, we can actually get started. The first thing I want to do is to filter our OTU table. So a common first step is when you're dealing with an OTU table is to get rid of undesirable entries, such as things that are empty across all samples, meaning it's not amplified or it's a blank or something. So here I'm showing how you can do that using a Pandas function called .all, which is very useful. The syntax is some criteria .all and then the axis. So in this case, I'm saying, go to my OTU table and go find everything where the entire row, meaning across all of my samples, is NA or not a number. So before we perform any operation, I'm just going to show you what that returns. So I've asked it to return .loc, or the row indices. So you can see that actually it didn't return anything, right? So that actually means that no OTUs actually have to be removed by this way. So now I'm going to actually show columns from the OTU table that have NA instead across all OTUs. So we first examined individual samples. Do we need to get rid of individual samples because there's no OTUs in them? Now we're going to go along the other axis and see if there's any OTU that's not present across all our samples. So let's take a look at that. So you see what I get is a list of the row indices and true or false. In this case, as expected, if your blank turns out the way a blank should, the blank has no OTUs in it. So we want to drop that. So here I'm declaring this Boolean object as, by some name that I can refer to. And I'm using the same kind of data structure we went over in Pandas part 1 to get rid of it. So in this case, I'm saying the columns that I want to keep are located, or the row indices, where this is false. So this should give me those row indexes that I would like to keep. The reason I do this instead of dropping is that it's much better for data traceability to keep a subset rather than to drop and alter things in place. So if I look at what that's returned, we see that the columns that I would like to keep are all of the sample IDs other than the blank. So now I use the Pandas data frame structure where I can select columns of the data frame by putting that list of columns inside the square brackets. So I'm saying now I'm setting OTU table to that subset of columns that I would like to keep. Again, if we imagine that this had been done the other way, let's say we made a mistake. If we had dropped that blank column in place, we would have no way to go back to the prior data steps. So that's, again, why it's always best practice to not do that if possible. So let's look at our new OTU table. And we see, indeed, that the blank is gone. So in our next step, we're doing another common operation, which is to get rid of so-called false sequences like chloroplasts, sometimes mitochondria. So in this case, I'm going to show how to use the Pandas string.contains function, which is really great because you can use it to actually search entire columns of your data frame at once for substrings. In this case, we're going to be searching .index, right? Because we've set the OTU ID as our index column. And a nice capability is that by using this function, you can actually search for multiple substrings at once, unlike in traditional Python where you'd have to actually loop through a list. So here I'm showing you how to do that. So I'm saying, show me the part of the OTU table in which the index of the OTU table contains either of these two terms. And I'm putting both of them here to cover all my bases because it is case specific. So let's take a look. And we see that, in fact, we do have chloroplasts, and that for one of our samples, it makes up quite a large, two of our samples makes up quite a hefty chunk of the OTU counts. So you can imagine that would be problematic for downstream data analysis. So now I'm going to use one of the methods we covered in part 1, which is to use the tilde to say, give me back everything that's not this thing. So I'm simply taking that search criteria that we used earlier and putting that tilde there to say, just give me back the part of the OTU table without the chloroplasts. Great. And here I'm showing that in addition to .isNA and some of these more specific functions I've been showing, you can use the same structure to filter with other criteria. So it's common, for example, when you're filtering an OTU table, that you have some sort of cutoff for the minimum number of reads that you would like to evaluate. So in this case, I'm saying, okay, now that I've filtered out all my NA stuff, I filter out all my chloroplasts, for everything that's left, I want to get rid of things that have less than 10 reads, or get rid of OTUs that have less than 10 reads in all of my samples. Meaning that overall in the system, they're probably not important. So here, I'm showing how to do that. So I'm doing my .loc, right? Which inside I've said, here's my criteria, less than 10. And I'm using the .all function again, because you don't want it to be the case that one sample has 10 OTUs, but another one might have a lot of it. So here, let's show that. So you can see very easily, let's take a look at our first one here. We see that, you know, the total is 3, 3, and 4, right? So then again, I'm gonna say, return to me what's not that, using the tilde function. Okay, so now we finished all our OTU cleanup. Now that everything has been filtered, I'm gonna finally arrive at my final goal of isolating only the photo autotrophs. So this is how you can isolate some groups of interest to you if you want to separate them from an OTU table. So I'm gonna actually use the string.contains function one more time to do this. And here I've done this 3 term search criteria, looking for cyanobacteria, green sulfur bacteria, and purple sulfur bacteria. And now let's take a look at that. So here we can see that we have all of our environmental samples. And if we look at our indices, we see that we only have our photoautotrophs. Then if we look at these numbers, we see that nothing is super low abundance. and that there are no NAs, so that all of our search criteria have worked. So now we've completed part 1 of this analysis. The next step is to set up our metadata table. So in this case, because this OTU table is a subset of a broader environmental survey, not all the sample information in the metadata table is relevant to the analysis. So we also have to filter the metadata table. So I'm going to use the pandas.drop function to basically get rid of any entries in the metadata table whose sample IDs are not in our OTU table. So here I've declared a list called toRemove, and I'm saying for each string in the metadata index column, which in this case corresponds to sample ID, if it is not in our OTU table column headers, append it to this list. And here I'm just printing S as I'm going along to show you that it corresponds to our environmental sample IDs. And these are the ones that have come back as toRemove. So now I'm declaring cleaned metadata table as equal to metadata.drop those. And again, I'm not dropping in place because that's bad practice in case you need to trace something. So that's why I've left the default in place equals false argument alone, and I've set it to a new object. So let's take a look at this now. And you see, when we review these indices, these row indices, it matches only what is occurring in the OTU columns. So now we have our clean metadata table. Let's take a look now again at our categorical data, which is what we'd be interested in for evaluating how OTU abundances are varying with environmental variables. So I have sulfide, particulate sulfur, and some other things. So now I'm going to show you how to actually take advantage of a Pandas function, which is called group by. And this is really great because you can use group by to basically go through each of these columns in the metadata table and then group your OTU data by each unique category in that column. So for example, I could say, okay, show me everything with low sulfide, show me everything with high sulfide, show me everything below the redox line. You know, so it's very useful. But the only thing that we need to do first is we have to reformat our OTU table such that the sample IDs are also the row indexes, because it must match the metadata column row indexing. And we can do this with another Pandas function called transpose, and that swaps the rows and the columns. So that's very easy to set up. It's just .t for transpose. And actually, I can show what that looks like in this empty cell at the bottom. So you can see now what's happened is that your row indices have become sample ID and your OTUs have become column ID. So now here's how we use group by. I'm saying for each of the OTUs that are now our columns, make a temporary data frame which takes only that OTU and its counts, that one column, and joins it to the metadata at the categorical level and join it along columns. So I'm basically saying take the OTU and its counts, stick it as a column onto the categorical metadata, and then starting at the second item in temp, because first will be the OTU. And then I'm saying for name, group by temp.group by C. So that's a lot, but it's going to basically show you the OTU counts and as joins to each discrete category of that metadata column. So let's see how that looks. Okay, so here I have my first OTU. And now it's going to print name, which in this case is the first discrete category of the sulfide column, sulfide 0. And then it's showing me these sample IDs and the OTUs counts. So then if I look at sulfide equals 1 or high sulfide, for example, you see that there's a lot of green sulfur bacteria in the high sulfide samples, which makes sense because they live in water with a lot of sulfide, whereas with this one, we see that they're not as abundant in the low sulfide categories. And then it's doing the same thing with particulate sulfur. So it's saying, here's your OTU counts grouped with low and so on. So to show you an example of how this can be useful, let's compare it to one of the OTUs with the cyanobacteria, because we wouldn't expect them to really live in water with sulfide. Here we go. So we can see here's sulfide category 0. And then if we compare that to sulfide category 1, actually, no, they're pretty even. But I mean, you get the point. The usefulness of this is that you can examine your OTU information in relationship to the discrete categories. So that is all I had for today with the Python notebook for Python Pandas Lesson 2. Thanks everyone for joining us, and we'll hope to see you next time.